Hardegree-Ullman.
Okay, great.
Well, hello, everybody. This is Scott Roberts from Explore Scientific and the Explore Alliance, and you are watching 7 Months of Science. This is the 7th month of 7 Months of Science, so I'm a little sad that we've come to the end. But Dr. Caitlin Ahrens has brought forth some incredible speakers to talk about all matter of our planetary systems and other worlds, life on other planets, and it's just a really incredible series. And if you get a chance, you'll want to go watch them all. Dr. Caitlin Ahrens is a planetary scientist. She's currently at NASA postdoctoral program. She's a NASA postdoctoral program. That's a mouthful, Caitlin. Fellow at Goddard Space Flight Center. She's also a member of the Diviner Science Team. In 2018, Dr. Ahrens received the 10 Outstanding Young Americans Award presented by the Jaycees for her efforts in science communication and outreach, which she's doing right now with the show. Her program, 7 Months of Science, has brought forth major scientists, as I just mentioned earlier, giving our audience great insights into the current understanding of other worlds. So, Caitlin, thank you so much for coming onto our program. Perhaps you can introduce your special guest for today's program.
Yes, it is my great honor and pleasure to welcome our last but not least speaker for 7 Months of Science. So I'm so excited to welcome Dr. Kevin Hardegree-Ullman. So just a little bit about him. His research focuses on the many different aspects of exoplanet science in order to gain a wide variety of planets beyond the solar system. So his work includes measuring precise stellar properties with an emphasis on the coldest stars, or dwarfs, exoplanet transit follow-up with ground and space-based telescopes, and monitoring variability on brown dwarfs. Kevin received his PhD from the University of Toledo in 2018 and was a postdoc at the NASA Exoplanet Science Institute at Caltech until he joined, wait for it, I really love this title and I cannot wait to say this, he joined the Alien Earthset team as a postdoc at the University of Arizona in 2021. So the stage is yours, Dr. Kevin Hardegree-Ullman.
Thank you so much, Caitlin, and thank you, Caitlin and Scott, and all the sponsors for having me, and thank you, everybody, for tuning in. I am Kevin Hardegree-Ullman, and I am an exoplaneteer. I study exoplanets and all of their wonderful goodness. So let me go ahead and get my presentation sharing. And all right. Is that the right view there?
Yep.
All right. So I will be talking tonight about the exoplanet revolution. Exoplanets have now been around for about 3 decades, about as long as I've been around. And we're at a point in history where at least in exoplanet science, where we are discovering just so many planets. And so now we're at a point where because we have these huge populations of planets, we can start to learn something about planets in specifically the galaxy and the greater universe. And so I want to pose a question to all of you watching. Why do we do this? What are the big reasons for studying planets beyond our solar system? I'm not going to answer this for you. I have many reasons why, but I think it's very exciting of the prospects of potentially finding life out there, learning about how planets form, what kind of planets are out there. As I will discuss later, a lot of the planets we found are unlike anything we have found in our own solar system. So speaking of the solar system, a lot of this research is made possible by our knowledge of the solar system. Unfortunately, that comes with the caveat of a very solar system centric biased view of the universe. Before we detected planets in other stellar systems, we thought, hey, all planet systems must form like our own. There must be these rocky inner planets with gas giants on the outside. This is a very solar system centric view of the universe. But what did we discover? Well, I'll talk about that a little bit. But first, I'll talk a little bit about a few detection methods. A couple of the most common ones. It would be fabulous if we could just go take a snapshot of these planets. And it is possible. There's a method called direct imaging. And direct imaging is just taking a snapshot of the planet. First, though, we have to block out the light from the host star because the stars are so much brighter than the planets. A great analogy that I've heard is it's like trying to image a firefly against a lighthouse. You somehow have to block out the light from the lighthouse that is 10,000, 100,000 times brighter than the firefly in order to actually see that firefly. And so the method of direct imaging, we have some clever instruments that block out the light from the host star as shown in this illustration, and we can see the planets. Once we're able to see the planets, we can constrain their mass and we can get a direct spectrum. We can figure out what these planets are composed of. However, we're currently limited to young planets, so planets that are a few millions, tens of millions of years old. And all of the direct image planets are giant planets on wide orbits, orbiting very far from their host star. And so there are limitations. We found about 50 directly imaged planets, but our technology is pushing toward smaller and closer in planets. Another major method that we use to detect planets is the radial velocity method. This nice illustration just shows sort of how we do this. Up in the left corner, we have a star with a planet orbiting. When you have two massive bodies orbiting in space, they orbit around a common center of mass. And here's just an edge-on view of what you're seeing up here. And when we look at the star, specifically when we take a spectrum of the star, we know that specific spectral features happen at specific wavelengths. And if we take a spectrum at different points in time, we can monitor minute shifts because the planet is tugging at the star. We can measure minute shifts. And that translates into being able to measure its mass. So we can calculate what's called the radial velocity. Once we have a radial velocity measurement, we can measure the minimum mass of the planet. If a planet is orbits edge on like this, we can measure its inclination angle with respect to the star and actually constrain fully its mass. But if it isn't in this edge-on geometry, we're limited. The radial velocity method does require bright stars, and so far, Earth-like planets are hard to detect. But again, we are pushing our technology to its limits. And then, kind of the workhorse these days, and I'll talk a lot about the transit method. This is when a planet, not in this geometry, it'll flip over in a second, with respect to our line of sight, transits in front of its host star. This allows us to measure the radius of the planet. However, the likelihood that a planet crosses in front of its host star is fairly low. So you have to observe a lot of different stars in order to detect even a single transit. So I'll talk a little bit more about that later. If you have a multiple planet system, multiple transiting planet system. This is what it looks like. Again, you have one planet, the star drops in brightness by a certain fraction proportional to the radius of the planet. And then sometimes, by chance, there might be two planets orbiting. So we get some funky shape in this brightness plot of the star. But we've detected many multiple planet systems, and those are very exciting systems to study. So there's a very, very interesting history of exoplanet discovery. I won't go into all of the details, but the people have been thinking about planets orbiting other stars for thousands of years, and that's a really exciting history. But I'll start back in 1988 with the potential first detection of an exoplanet. There was a previous claim in about the 1950s, but it was later determined that that was just instrumental effects. So the first honest claim, good claim, was in 1988 with Gamma Cephei AB. So the nomenclature for exoplanets, if it's the host star name, and then the first planet detected is given the letter B, the second planet C, so on and so forth. This so happened to orbit in a binary star system. So the capital A is for the primary star in that system, then the lowercase b is the planet. So this was detected using the radial velocity method. If you look with your eye, you can maybe see sort of that wave sinusoidal type pattern. But the people who made this discovery weren't very confident in their results. So they actually retracted this discovery in 1992. But in 2002, a decade later, more data had been taken, and they were actually able to confirm this planet in 2002. So this planet has a mass, a minimum mass of about 1.5 Jupiter masses on an orbit at about the location of Mars. The host star, though, is a giant star. So it's kind of a weird situation, not quite anything that we would necessarily expect. The following year, there was a claim of a minimum 11 Jupiter mass planet. This time it's very conclusive. There's a lot of data. There's a wavy pattern because the planet orbits in kind of in an eccentric orbit. That's why it's not perfectly sinusoidal. It looks more like a wavy pattern. So this was an early detection. This also orbits in a binary system around a late F star, so not quite like our sun. But this particular planet in 2019, 30 years after its discovery, with the Gaia mission, the European Gaia mission, they actually were able to measure an inclination angle of this planet. And it turns out this isn't actually a planet. This planet has a mass of about 107 Jupiter masses, placing it the size of a small star. So this is actually a star that was detected in 1989. So sometimes it takes a very long time to make sure that what you're seeing is actually what you're seeing. And so with more data, we refined this is not actually a planet. Then planets started gaining a little bit more traction with this discovery. These were pulsar planets. Pulsar is a dead rotating star, either a neutron star or a white dwarf, and it's very rapidly rotating. And it's, as this cartoon is showing, it's emitting radiation at its poles. And if the poles are oriented in the right geometry that we can view it on Earth, we can measure a rotation signal. What happened is these folks monitoring this pulsar, after removing the rotation signal, they noticed in this top panel that there's some sort of periodic signal in the data after fitting a rotation signal. And so they went ahead and fit a 98.2 day orbit in addition to the rotation signal. And then again, they fit a 66-day orbit with the rotation signal. And so it turns out there are 2 planets. After fitting 2 planet orbits and the rotation signal, here are the residuals. They're nice and flat, as you would expect, but there are two planets that are both about 4 Earth masses in the system. A couple of years later, a 3rd planet, about twice the mass of the moon, was discovered a couple of years later in the data. So these were exciting discoveries, but it completely threw off our notions of planet formation and how planets could actually survive the death of their star, because these were planets around a dead star, which is really cool. Then in 1995, because again, we are very solar system centric, the discovery of a planet around a sun-like star, a G-type star, 51 Pegasi b, about half a Jupiter mass, orbiting every 4 days, was discovered. And you might have heard this particular discovery won the Nobel Prize in Physics in 2019. Again, it's a fantastic discovery, but there might have been a few discoveries before it. But again, with our very solar system centered views, this planet has a huge claim to fame. So what has happened in the following 30 years of discovery? Well, a lot. I will start with the detections of planets. How many planets have we detected? So this is just a timeline from 1989 to 2018 of what we've seen. And so in 1989, this was the now no longer a planet discovery, but this plot was made before that. 1992, the first planet around a pulsar. And then we slowly get a few more discoveries. The color of each bar is the detection method. I talked about radial velocity and transits. There are a few other detection methods, but radial velocity and transits are by far the most common. And so slowly, you'll notice that we're discovering a lot of planets with the radial velocity method up through the early 2000s. In 2002, the first planet was discovered transiting. And so you'll slowly notice that the transiting planets are gaining a lot more traction. Radial velocity is still the dominant detection method. But in 2009, the Kepler Space Telescope was launched. And then something happened in 2014. Kepler launched in 2009. There was a huge announcement in 2014 of 725 new planets. So transits just got a significant boost, completely obliterating the sort of record from radial velocity and kind of took over as the main detection method. There was another huge data release in 2016 where over nearly 1,300 new planets. So there was another spike in planets. And as of 2018, there were 3,800 planet detections. Here is an up-to-date plot of what I was showing in the previous slide. To date, there have been 4,566 confirmed planets. And confirming a planet requires follow-up observations and validation with statistics in some cases. And so these major data dumps where we just confirmed 1,000 planets, a lot of those systems were statistically validated. We have to prove that this is most likely a real planet in this scenario, and there are different tests we can do to confirm that. Otherwise, you just use a different detection method. If you're looking at a transiting planet and you're able to get radial velocity measurements and constrain the mass, you can confirm a planet that way too. So I brought up the Kepler mission. Kepler was a fabulous mission between 2009 and 2013 with the goal, and it was designed to detect Earth-like planets around Sun-like stars. So the transit method, if you want to confirm a planet, you have to see a transit 3 times. The first one to detect a signal, the second transit to just confirm that there's something sort of periodic, and then a third planet or a third transit to confirm that it's both a periodic signal and that the transit depth is the same, so that it's not just maybe another planet in the system or an anomaly or something like that. And so if you want to confirm an Earth-like planet around a Sun-like star, well, you need to stare at a Sun-like star for 365 days and see the planet transit 3 times. As I mentioned earlier, there's a very low probability of any given planet transiting its host star with respect to our line of sight. So you go look at 200,000 stars, and then maybe you'll be able to see a few Earths around a Sun-like star. Turns out, again, with our solar system-centric views, we were basing how active or quiet suns would be, or other stars would be, based on our own sun. So it turns out our sun is actually a little bit more quiet than your average star. And so we didn't quite detect an Earth-like planet around a Sun-like star, but Kepler nonetheless was groundbreaking to help us push toward finding other Earths. In 2013, 2 of Kepler's 4 stabilization gyroscopes failed, and you need at least 3 in order to point directly at this patch of sky. And this patch of sky here is roughly the size of two Big Dipper bowls. Each of these little squares here is about the size of a full moon. And so that's how big of the patch of sky that Kepler stared at for 4 years. But after its gyroscopes failed, it could no longer keep pointed precisely at that field. So what happened is some clever engineers figured out how to make K2 work again. And so, or Kepler worked again with the mission K2. Using a clever trick, they realized they could use the sun, radiation pressure from the sun, as a third stabilization axis. So if they're able to point at a particular patch of sky for about 80 days at a time with the sun at its back, and then it would have to rotate because it's trailing Earth in its orbit, it would have to rotate the spacecraft using its little thrusters to keep it precisely oriented at a different patch of the sky every 80 days, therefore extending the Kepler mission for another 4 years. This is another cartoony concept, just showing how big the K2 fields were with respect to the sky. And so every 80 days it would rotate and look at different patches of the sky. And so here's what it observed. Campaign 0 through 19. Campaign 0 was a test engineering proof of concept, so we didn't get too much good data there. And then campaign 18 was really its last full campaign before the fuel for the thrusters ran out. So the Kepler telescope was retired in 2018, but not before giving us loads of fantastic data. Then we have, the video that brought us in was all about the Tess mission. Tess is looking at even more of the sky. The Transiting Exoplanet Survey satellite is currently operated, and it probably won't have the same types of spacecraft anomalies as Kepler, so it could potentially go on for many, many, many years. But Tess is a little bit different of a concept. It's staring at a large patch of sky every 27 days and then rotating. So for the first year of Tess's operation, it observed the southern portion of the sky. And so there are some areas that were observed continuously in what's called the continuous viewing zones for nearly a year, and a lot of other portions of the sky for only 27 days. But then after its first year, it flipped to the northern hemisphere. You'll notice a big patch, a big hole missing in the sky. In their first year of operations, they realized they were getting a lot of stray light from the sun in certain regions. So they had to sort of retool their operations for the second year. And so some of the sky was not observed. But nonetheless, Tess has been continuously monitoring a different large patch of the sky, way bigger than the patch that Kepler or K2 could observe. And we'll see what comes about from Tess. I want to show you a really cool animation, putting real data, just showing you what Tess looked at, and showing you a phenomenal view of the galaxy from the viewpoint of Tess. I just love this so much. It's incredible what Tess has done, and I'll let it run through again. But every 27 days, it's rotating to a new sector, and I think it's in its 43rd or so sector right now. So we're reobserving certain patches, we're filling in some of the gaps, and we're discovering all sorts of new planets. So I've talked about the detection methods, some of the very important spacecrafts to get us all sorts of new planets. But now I want to talk a little bit about physical properties of the planets. What have we seen in these planets? And so first I want to show what planets are we finding. This again steps through time, showing on the x-axis orbital period, and then the planet mass in terms of Jupiter masses. And I've plotted on here the solar system planets. A lot of the early detections were these larger planets. And it wasn't until after the Kepler spacecraft launched that we got a lot of the smaller planets. But what you'll notice in this plot is we haven't quite found any planets that are quite like Earth, that orbit quite, well, we found a lot of planets that orbit out at Earth, but not quite the same mass as Earth. There are three major blobs here, a lot of the radial velocity planets. There's a large chunk at large orbital periods and large masses. As I mentioned earlier, these little squares here are direct imaging. So these planets are really far from their star, and they're pretty big planets. They're pretty massive planets. Then we have a population of what we call hot Jupiters, Jupiter size or mass planets orbiting very close to their star. This was very weird to us when we first discovered them. Why are these massive planets orbiting so close to their sun? We only have Jupiter orbiting really, really far away. So this was very curious discovery. Turns out some of that is just a detection bias. It's very easy to find close-in things that are large close-in things to their host star that are large. But then Kepler came along and we started pushing the limits. We've discovered smaller planets, but we are limited a little bit by how long we can stare at individual stars. Placing basically the same plot, but now with respect to Earth radii. We have our solar system planets again. A lot of our early detections are basically these Jupiter-sized things. And then we'll see a lot of the early transit work was very short, very large planets. And then large Kepler data dumps just fill in those gaps. And you might notice here, Uranus and Neptune and Earth and Venus down here. a majority of the planets that we're discovering are unlike anything in our own solar system. This was a phenomenal discovery. Again, just completely throwing out our solar system centric view of the universe. Most of the planets, we don't have anything like them in our own solar system. So that kind of puts us in our place. Once you have both mass and radius measured, we don't have them for all of the planets shown on the previous plot. A lot of those were extrapolations to either radius or mass. But once we had the transit method locked down as our main method of discovering planets, a lot of those can be followed up with our radial velocity instruments. So we can measure both mass and radius, which gives us a density of the planet. And then we can start to learn something about the properties of these planets. And so this particular plot shows mass versus radius. And then we have Venus and Earth and Uranus and Neptune plotted here. And then these tracks are just models. If a planet was completely iron, we would expect a planet to follow this lower track. More rocky planets, very much like Earth, follow this dotted track. And then if it was a completely water world, it would follow this nice dashed line. And then larger planets with more of a thick hydrogen atmosphere are above this line. So we can begin to learn about the properties of these planets. Something that's also useful is monitoring these planets at different wavelengths. Then we can begin to learn something about the atmosphere of these planets. This is called transmission spectroscopy. And transmission spectroscopy tells us something about what's in the atmosphere of these planets. And so I'll show you this animation. We observe a transit of a planet at different wavelengths, and you'll see a different transit depth because you're seeing through different layers of the atmosphere at these different wavelengths. And so we can begin to learn a little bit about the atmosphere. And so this is some real data of hot Jupiter planets. So these planets that orbit really close to their star, but we've looked at these planets at transiting at many different wavelengths, and we can begin to figure out what's in the atmosphere of these. And so there's a nice water feature that some of these planets have. Typically, we observe around this water feature with the Hubble telescope. And then at more of these optical wavelengths down here, we observe with ground-based telescopes and sometimes space-based telescopes. I think a lot of this data was with the Hubble Space Telescope. But no two planets look exactly alike. There are all sorts of different things going on in the atmospheres of these planets. So these hot Jupiters are diverse in their atmosphere properties. And with the James Webb Space Telescope launching, hopefully next month, fingers crossed, one of the major goals in exoplanet science is to get atmosphere information from smaller and smaller planets. So hopefully we'll learn about the diversity of these atmospheres from smaller and smaller planets. But you can't talk about exoplanets without talking about the stars. You have to know the stars very well to know anything about the planet. If it's the radial velocity method, you have to know the mass of the host star in order to get the mass of the planet. If it's the transit method, you have to know the radius of the star in order to know the radius of the planet. And so a lot of the exoplanet focus has been on sun-like stars, so F, G, and K type stars around the temperature and size of the sun. This was the main focus of the Kepler mission, and there was a phenomenal result from the Kepler mission. With precise stellar radius measurements, there's what we call the planet radius valley. And so here we have just number of planets per star. And then on the x-axis here, we have planet size, and I've just plotted over here Earth and Neptune. And then a majority of our planets fall between the size of Earth, and Neptune. And between them, there's actually a gap. There's a smaller abundance of planets, around 1.8 or 2 Earth radii. And this was only made possible by measuring very precisely the stellar radii, which propagates to a more precise planet radius. And so this top plot just shows stellar radii once we had temperatures and got a radius measurement from spectra. And then a couple of years later, the Gaia mission allowed us to get distances, only refining our stellar radii, getting smaller uncertainties on radius measurements. The planet radius valley still exists at the same place with just much better precision on radius measurements. But the radius valley only emerged. There was some theoretical work predicting this radius valley to happen, showing that mostly planets that are smaller than where this gap is are most likely to be rocky or super Earths, rocky super Earths, and planets above this gap are more likely to be sub or mini Neptunes with a more gaseous atmosphere. And so this was a very exciting result. But what about the M dwarfs? I care a lot about M dwarfs. M dwarfs are really cool stars, no pun intended. We have here just a real size diagram of the sun compared to the size of Earth, but then 2 M dwarfs. M dwarfs span a large size range. So an early M dwarf is about half the radius of the sun, and a late M dwarf is about a tenth the size of the sun. And again, I've plotted Earth on top of these stars. It's potentially a lot easier to detect an Earth-sized planet around a cool star. So what are some advantages of these M dwarfs? Well, M dwarfs are 70% of the stars in the galaxy, so they're far more abundant. M dwarfs also don't burn through their fuel nearly as fast as sun-like stars, so they live forever, mostly forever. There's a greater planet-to-star ratio. In this plot, we just have nice transit plots and the star brightness. So up here at the top, you see how much of a drop an Earth-sized planet around the sun would drop. So this is a 0.01% drop in brightness. This is very, very hard to measure, and you need something like the Kepler telescope and a fairly quiet star in order to measure something that precise. But if you have an Earth orbiting an M dwarf, you get something much, much deeper. So, I mean, I say much, but this is a 0.5% dip as opposed to a 0.01% dip. This can go, depending on the size of your star, this can go down to 1%, which is what we measure if Jupiter is orbiting a sun-like star. A lot of the Jupiter-sized planets that we've measured transits for have a 1% drop in brightness. And you can do this if you have a decent camera on your telescopes at home. And so you can measure a 1% drop in brightness fairly easily. M dwarf planets also have higher radial velocity amplitudes, making Earth-sized planets easier to find around M dwarfs. And what we call the habitable zone, which at the moment I'll very loosely define as water, the zone in which liquid water can exist around a star. I'll get back to that in a minute. But the habitable zones around M dwarfs are much closer. So if we have a time-limited survey and can only observe some stars, M dwarfs are the things to look for habitable zone planets. M dwarfs have some disadvantages though. Most M dwarfs are very faint, a lot fainter than your typical sun-like star, and M dwarfs are very active. So we're not sure how activity plays a role in shaping the atmospheres and potentially life formation on these planets. But M dwarfs, if they're old enough, they aren't as active. So it's possible that if planets and their atmospheres survive through the very active phase of M dwarfs, maybe life could exist. But what we found with the Kepler data specifically is that planets are more common around M dwarfs. So this is a nice plot of the star type. versus number of planets per star. And there have been many, many different surveys, so they all use somewhat different methods, but the measurements are fairly consistent that within an orbital period of 50 days, there are fewer planets around these sun-like stars than there are around M dwarfs. Any given M dwarf has 1 to 2 planets orbiting within 50 days. And so M dwarfs have more planets in general. We also have something to be excited about. Our closest neighbor is Proxima Centauri. It's an M dwarf. And in 2016, there was a planet slightly more massive than Earth found roughly in the habitable zone of Proxima Centauri. So our closest neighbor is an M dwarf, and it has a roughly Earth-sized planet. So maybe in 100 years, we could actually get something over there and take an image. Proxima Centauri is very exciting prospects. We'll see what happens in the future. And then there's also the Trappist1 system, which you may have heard about in the media. This is a very late type M dwarf. It's basically a star at the border between what we call stars and brown dwarfs. But this was a really exciting discovery. It was a ground-based telescope survey looking at these cool stars and searching for transiting planets. They found like 3 or 4 of these transiting planets. Then they applied for time on the Spitzer Space Telescope and observed this star continuously for many, many days and discovered a few more planets. And so this particular system has 7 Earth-sized planets around this one star, which is incredibly exciting. I love this graphic. It shows that a couple of the planets are a bit too hot. Liquid water probably couldn't exist there, but 2 or 3 of these planets could potentially host liquid water. And a couple of these planets are a little too cold. So this particular system has all sorts of exciting things going for it. And there's a lot of follow-up that can be done with this. And we really want to constrain, now that we know the sizes of the planets with transits. It's a little bit tougher because the host star is a little bit fainter to get masses for these things. But we have constrained the masses to a degree, and we're trying to figure out everything we can about these planets. And so Trappist1 is very exciting. But I talked about habitability. Habitability is more than just, can liquid water exist? So this is a plot sort of outlining all the things that go into actually determining whether or not a planet is habitable, from stellar effects to planetary properties and the planetary system itself. These things in blue, you can actually measure these properties, but the other properties are things we either have to have better instruments or more sensitive instruments, or we have to extrapolate somehow. So we can't measure all of these properties, but it takes a lot to actually make a claim that a planet is habitable. If you see any news article that says habitable planet, ignore it. It's probably going overboard, trying to sell you something. What they most likely mean is that it's within the habitable zone where liquid water could exist. That's about as far as most of these habitability claims go in any discovery paper. But there are a lot of fabulous scientists working on all of these different aspects of what goes into habitability. And hopefully someday soon, we can actually make a claim that these planets are truly habitable. I've done a little bit of work on K2. K2 was maybe a little bit more exciting than Kepler. Kepler stared at 200 to 300,000 stars in one little patch of sky. This is an illustration of the galaxy. There's the disk, the bulge, and then this is the patch where Kepler stared, and K2 stared at all different portions of the galaxy. So we're actually able to probe things about planets in different areas of the galaxy, which is potentially more exciting. but you'll notice a big patch of red. K2 observed many, many more M dwarfs, and this next plot shows that K2 observed 15 times more M dwarfs than Kepler. Kepler, again, was designed to look at sun-like stars, so that's where you see this big peak here, around between 5 and 6,000 Kelvin. There's most of the stars that Kepler targeted were between there, but K2 observed 15 times more. That's partly because K2 was guest observer driven, so scientists were able to propose targets to go look at with K2. So that's why there was more emphasis on M dwarfs. Here's an awesome plot from a paper that we just had published. This is showing the difference between the Kepler and K2 planet populations so far. It's on the x-axis are planet radius, and I've shown Earth, Neptune, and Jupiter. And then the magnitude or brightness of the star. A majority of the Kepler targets are tougher to follow up with ground-based observations. A lot of our instruments that are trying to measure masses, the targets have to be brighter than 13th or 14th magnitude. So that sort of limits our population. K2, our paper, we just uniformly detected 747 planets, including 366 new candidates that had never been identified before. And many of the K2 targets are a little bit brighter, but the color of the points indicate the host star temperature. So things below 4,000 Kelvin are M dwarf planets, and you see a nice healthy dose of M dwarf planets. And again, both plots show that a majority of the planets are between the size of Earth and Neptune. And so just a little bit of difference, but a little bit more M dwarf planets with K2. And here's some results from some of my work. K2, again, probed different patches of the sky. So there was a question as to whether or not the planet radius valley is specific to this location of sky that Kepler looked at, or is it just kind of a thing that happens throughout the galaxy. And so deriving uniform stellar radii, I was able to uniformly derive planet radii, and lo and behold, we see a planet radius valley roughly where Kepler found one too. And so that's exciting that this planet radius valley, there's a lack of roughly 2 Earth radius planets all throughout the galaxy, which is kind of cool. But what can you do with citizen science projects? There's always some exciting citizen science projects going on. One that I want to talk about is Planet Hunters Tess. You can go to Planet Hunters Tess and join the search for undiscovered worlds. Since Tess is ongoing, there will regularly be new data. This is where you can learn how to classify stars. They've already done the legwork of processing the data, but this, you can learn how to identify planet signals. So you can potentially discover new worlds on your own. This has been done with Kepler. There was a Planet Hunters Kepler. Some of my colleagues, when we were working on K2 data, we had exoplanet explorers to identify new planets in K2. And Planet Hunters Tess is the latest iteration of that. And so go check it out and go help find some new test planets. Additionally, if you have your own telescopes at home and you have a camera for that telescope, you can join Exoplanet Watch. This is run by some of my colleagues at the Jet Propulsion Laboratory, where you can collect data. They do have a way that you can process the data with their pipeline, and then you can basically update properties of these exoplanets with your own resources. And so this is a really cool thing to just get the latest properties for these exoplanets using from your own data. And so I encourage you to check this out too. And then I will end with a couple of cool videos. I've worked on a system that was an original citizen science discovery. So I will play this video and then I will talk about the really cool citizen science discovery. This is K2138, a 6-planet system. So that was K2138, a 6-planet system. This planet system was discovered through our Exoplanet Explorers Citizen Science Project. And Exoplanet Explorers was actually featured on Stargazing Live, a program run by Brian Cox in Australia. And the citizen scientists were able to go through the data and they identified a planet system with 4 planets. The first day they were taught how to use the system. The second day more just talking about how it works. And then the third day they wanted to announce a discovery. So the citizen scientists had discovered a 4-planet system. And then when the scientists were looking through the data, they actually detected another planet after removing the signals from the first 4. And then, so they discovered a 5th planet. And then they discovered evidence for a 6th planet, this outer planet that you see here. And so this outer planet, there were only 2 transits. As I mentioned earlier, to confirm that it's a planet, you have to have 3. So what we did was observe where this predicted transit was going to happen using the Spitzer Space Telescope, and we confirmed this planet. The cool thing about this system is that these inner planets orbit in orbital resonances. So like for every 2 orbits or 3 orbits of the inner planet, the outer planet orbits twice, and so on and so forth. So they're able to do something called sonification, which is what you hear with this nice, cool video. And then this outer planet orbits kind of near resonance, but there's a large gap between the 5th planet and the 6th planet. So it's possible that there might be other planets hiding in between this gap that are non-transiting. And so this was done, created by System Sounds, and I'll show another video in a second about that. So the past, present, and future of exoplanets are very exciting. I won't go through this whole plot, but Hubble, Kepler, Gaia, Tess, the James Webb Space Telescope, and then a few other European missions, Cheops, Plato, and Ariel, are going to be crucial for exoplanets in the near future. And so I want to end with another sonification of our exoplanet discoveries through time. right, and I'll leave you with that. Thank you so much.
Wow, that was amazing.
That was gorgeous. Oh my goodness gracious. Ah, the symphony of planets. But how exciting to have citizen science to also discover a planetary system and to then have scientists bring forth that discovery as well. I think citizen science is still a fairly new dynamic
Oh,
between communities and scientists.
it's
But to
absolutely
see,
amazing.
yeah,
We had another, through the Exoplanet Explorers project, I worked on a small paper where we wanted to release more planets. So we released, I think, about 30 planet candidates from citizen scientist discoveries that we just wanted to put out there, because if you help discover these planets, you get your name on a scientific publication. Like, you definitely get the credit that you deserve. So these are fabulous opportunities.
That's great. That's great. There are a couple of questions here. Harold Locke, watching on YouTube, says, does the spectroscopy find the same elements as we have here to support life? And are those conditions deemed necessary?
That is a fantastic question. And that is what we are pushing toward. As I mentioned, with those hot Jupiters, there's a nice water feature at infrared wavelengths. That'll be very important to look for with future missions. We're trying to push toward these Earth-sized planets. We really want to see what's in the atmosphere of these Earth-like planets. And I think maybe in the next decade or two, we'll probably be able to say, hopefully, that there's evidence that life could be supported on some of these planets. But we're not quite there yet.
Mm-hmm. Mm-hmm. Martin Eastburn, watching on YouTube, says, why are most of the discoveries outside of the Milky Way?
These discoveries are within our own
Milky Way, right?
A lot of the planets are fairly close by, within a few hundred parsecs of the sun. There was a claim, I think, within the last week or two, of a planet outside of our galaxy using a method that I didn't talk about, but it's really cool. You should go check it out. Check out the gravitational microlensing method. That's one of the few ways that we might be able to detect planets beyond our galaxy, but it's really, really tough to really say. But all of these discoveries that were presented today are within our own galaxy.
Harold Locke comments. He says, "I've been reading that what they believe to be older planets, that their sun has been absorbing the metals and elements before going supernova. I guess some sort of transference of materials or something."
Yeah, some of these stars, especially if they get through the red giant phase, they're expanding, they're eating their planets. There are some papers that are coming out about these planets found around white dwarfs that might be metal enhanced because they ate some of their rocky planets. And so those are really exciting. We can learn about all the different stages of the planet life cycle by studying some of these stars and in these different systems.
Yeah, and I have a question. I mean, how many exoplanets have we done some statistical analysis or something to try to infer how many exoplanets that the Milky Way itself may have?
That is a good question, and I don't have the exact number, but there have been extrapolations. Pretty much, we expect almost all stars to have planets, just based on what we have seen so far. All of these M dwarfs probably have a couple of planets, but that's that's sort of an extrapolation based on the data that we have. Have we detected or actually seen a planet around every single star? No, because either it's not in the right transiting geometry, or our instruments can't measure a mass or whatever. But we now have a statistical population that we can extrapolate. We can make these educated guesses as to how many planets are out there. And we think that probably most stars could have a planet around them, at least one planet, in many cases more.
It makes me wonder what our sun would look like from the distances that we're finding exoplanets out. If we could flip that around and with the instruments that we have, with the methods that we use, what would we see of our sun and its planets?
Yeah, and there are
Would we just
actually
see Jupiter and Saturn, or do you think that we could get down to the rocky planets?
Definitely, and I think there are a few scientists working on. They have definitely done that flipping of things. They're like, what star systems could actually see us?
Yeah.
And so let's go look at those things and see if we can see signs of planets that could be like Earth-like around them, and see if they have aliens looking back at us trying to detect the same thing. So there is a population of stars that could see us, which is really cool.
Right.
Oh, that's so fascinating. I have a quick question. I know it's definitely hard to pick a favorite as far as space telescopes go, but do you have a favorite of ground-based telescopes?
Ooh, that's a tough one. I'm on the scientific board of a telescope in Chile that I shall not be named, but I have a soft spot for telescopes that are 4 meters in size, because I've collected a lot of data at 4-meter class telescopes. So I've used the Wind telescope on Kitt Peak a lot. I've used the SOAR telescope in Chile a lot. I've used the Lowell Discovery telescope in Flagstaff. So I really like 4-meter class telescopes, but any telescope that I go to, I've been to all sizes and used all different sizes. So it's really hard to choose a favorite ground-based one.
For sure. We all have our favorites. Very much like we all have our favorite, backyard telescopes. We all have our favorite brands that we like to use, or maybe certain size eyepieces and whatnot. We all have our favorite of techniques as well. So do you prefer like radial velocity or micro lensing techniques?
Yeah, definitely. I think I'm partial to transit, but that's only because that's the one that I've done the most. But you can get different information from different techniques, and if you can use multiple techniques together, you can learn so much more.
For sure. Another quick question too. Is there the possibility of detecting exomoons in the future?
In the future, yes, I really think so. There have been a couple of claims. It's really hard to detect, say, an Earth-sized planet. It's even harder to detect something smaller, such as a moon. So again, this is where we're pushing the limits, and hopefully we'll see some conclusive discoveries. There have been a few claims in the literature, and they're very exciting, but confidence, I don't think, is quite there yet to say we've definitely discovered another moon. But another moon could be another factor in habitability, because we have our own moon, and it plays an important role in say our oceans. So maybe that has something to do with life. We just don't know. But moons would definitely be something on my list to look forward to in the next few to 10 years.
Oh, I'm sure you have a to-do list already of what do we expect in the next decade or a couple decades. The Astro 2020 decadal is upon us as well too. So I'm sure exoplanetary communities are definitely getting ready for that as well. So very, very exciting stuff all the way around.
Yeah.
Well, great. Well, it's been a true honor and a pleasure to have you make all these presentations, Caitlin. Thank you so much. Kevin, I love the subject of exoplanets. You know, it's amazing that in in just a few short years, what it's been 20, 30 years that we've even discovered them. So, you know, that is something in my childhood and my young adult life. It was just, yeah, we think that they're out there. You know, it's kind of like the same thought a lot of us have now that, yeah, life must exist elsewhere in the universe. We don't know yet, okay? I think that a lot of scientists are working very hard to get at that and see if they can detect maybe spectral traces of life, something like that. I think that that might be one of the very first breakthroughs that we have, unless we dig up something on Mars, you know, so we'll see what happens there.
We'll see. There's a lot of really cool solar system science, and maybe our best bet is on one of these moons of one of the gas giants. That would be
Yeah,
and exciting.
that's a lot of scientists at JPL are banking on that one. So,
Oh yeah.
yeah. And I would say, you know, when I look at astronomical science, you know, from going of just plotting the stars to make maps, and then to try to determine distance, you know, to spectral analysis to understand, you know, the physics behind, you know, then the chemistry behind, you know, what makes up our stars and cosmos. To now, it seems that the search for life is a pretty strong influence on scientists today.
Most definitely.
Yeah.
That's one of the main drivers. When I pose the question why, that's probably at the top of many people's lists, is the search for life.
Yeah.
And we now know that planets are abundant. Now the question becomes, can any of those support life?
Right. Wonderful. Well, again, Caitlin, thank you so much for bringing all, you know, this rich treasure of science to us in 7 months of science. I really do hope that once you take a breather, that you come back with something at least on par with what you've done in this series of programs. I'm sure you will. You know, and again,
I need a long winter's nap. That's what I need.
a lot
And
of
you know
people
what?
are saying
We
that.
timed it perfectly that the last month of 7 months of science ended in November.
Right.
So it's been a fantastic, adventurous 7 months of science. I'm so excited that Kevin got to, you know, give us a strong ending for this too. So thank you again, Dr. Hardegree-Ullman, for your fantastic talk on exoplanets. It's been so exciting to hear all the different kinds of topics and just the variety of astronomers, and whether it's planetary scientists, exoplanetary, we've had astrophysics people, we've also had habitability people on here too. So as very much as with citizen science and also amateur astronomers, it's such a varied community, and this is very, very exciting of just how dynamic the astronomical community can be.
Mhm.
Wonderful. Yeah, and it's exciting to me too to see. I mean, you guys are young, vibrant people that have lots of energy, and I think that you're going to make. And you're on an amazing adventure. You know, an amazing journey, and I think that humanity's blessed to have really brilliant and driven people like yourselves to help us figure out these really tough questions. So thank you.
Thank you.
All right. I guess we will close our program. We have, of course, more programs coming up with Explore Alliance, including next Tuesday will be the 73rd Global Star Party, and it concurs with the Leonid meteor shower. Okay, so the theme is falling stars. All right, so we'll see what our lineup of speakers do, but we have astronomers already signing up for it, and so it should be pretty cool. So thank you again, and you guys keep looking up. And is there any closing statement you'd like to say, Caitlin?
Just thank you so much again for all of our wonderful viewers for the past 7 months, and I keep looking out for more Explorer Alliance live streams as well. They happen very regularly. There's also a calendar on the website as well. So keep tuning in, and you never know what kind of show you're going to tune in for.
That's true. We try to keep it fresh. So thank you so much. Thanks, Kevin. Very, very interesting. Take care, man.
Thank you.
Bye-bye. Bye, Kate.
Bye.